Hi, my name is Cody Castaneda, and today I will be walking you through problem 474. A spring-loaded piston cylinder device contains 1 kilogram of carbon dioxide. The system is heated from 100 kPa and 25 degrees Celsius to 1000 kPa and 300 degrees Celsius. Determine the total heat transfer to and work produced by the system. Because this is an ideal gas, we can use the ideal gas laws. Let's start by defining our volume at each state. At state 1, let's write out the ideal gas equation first. PV, pressure times volume, equals the mass times the gas constant times the temperature. Remember that when using this, your temperature needs to be in Rankine for English units or Kelvin for SI units. So, writing this out, we get 100,000 pascals times the volume, which is what we're going to solve for, equals M, which is the 1 kilogram, R, which is your ideal gas constant, which we'll find on table A2, and the ideal gas constant for carbon dioxide is 0.1889 kJ kilojoules a kilogram Kelvin. Using this, we need to multiply it by 1,000 because we put pascals in base Pascal unit, so we need this in base Joule unit, which would be 188.9 times our temperature, which is 25 degrees Celsius, but we need it in Kelvin, so 25 plus 273 gives us 298 Kelvin. Solving for V in this equation, we find that our volume at state 1 is equal to 0.5629 meters cubed. Now, let's do the same and find our volume for state 2. Using our same equation, PV equals MRT, our mass does not change and our R does not change. Essentially, we get that our volume is equal to our mass, which is 1 kilogram, times our ideal gas constant, which is the exact same and has a value of, exact same as state 1, it has a value of 188.9 joules per kilogram Kelvin, and our temperature, which is 300 degrees Celsius for state 2, plus 273 because we need to convert it to Kelvin. And then we divide that by our pressure, which was 1,000 kPa, and turns into 1 million pascals. Solving for this, we see that our volume 2 is equal to 0.1082 meters cubed. Using the values that we've obtained, we can use the linear increase in pressure formula to find the work done by the system. The work done by the system is equal to P1 plus P2 over 2 times the change in volume. Plugging in our values, we get the W equals 100 kPa, which is 100,000 pascals, plus 1,000 kPa, which is 1,000,000 pascals, over 2, minus our two volumes, or multiplied by the difference in our two volumes. Solving this equation, we get that work is equal to negative 250 and 85 joules, or 250.085 kilojoules. Because our work is negative, that means that it is work done by the system. So W out equals 250.085 kilojoules. And that is our answer for the first question. To find the difference in the change in heat throughout the system, we use the equation delta U plus W equals delta H, where delta H is the change in heat for the system. From our formula sheet, we know that delta U is equal to CV delta T, which is T1 minus T2. T1. Again, using table A2, we find that CV is equal to 0.657 kilojoules a kilogram Kelvin. Now, plugging in our values, we get that delta U equals 0.657 times 1,000, because we're converting kilojoules to joules, multiplied by the difference in temperature, which is 300 minus 25 degrees Celsius. This value is for state 2. This value is for state 1. We multiply here by 1,000, like I said, to convert kilojoules to joules. And for the temperature, we need not convert to Kelvin due to the fact that the difference would be the same between the both temperatures. Calculating this equation, we get that delta U equals 180,675 joules. Going back to our original equation of delta H equals delta U plus the work done, we get that delta H equals 180,675 joules plus our negative work, which was negative 250.085 kilojoules. Adding these two values together, we get that our delta H, which is equal to our change in heat, equals negative 69,410 joules. Because this is negative, this is equal to Q out. Summing up our problem, we have W out is equal to 250.085 kilojoules, and that Q out, or heat out, is equal to 69.410 kilojoules. Thank you for listening to me, and this has been problem 474.